First of all, I'd like to thank the organisers for kindly inviting me to this wonderful event. It's lovely to be here, and for the beautiful weather which they've arranged for us as well. So I'm Raphaël, Clifford from the University of Bristol. This is a combination of joint work, sometimes just with Marcus Gelsenius and sometimes with both Marcus Gelsenius and Benjamin Sach. I can sort of feel an echo. Can other people hear an echo when I speak? Is it all right? Okay. Right. So let me try and tell you what I'm going to talk about. So this is going to be talk about unconditional lower bounds, so a slight change from the conditional lower bounds. And generally speaking, it's going to be about streaming problems. And the talk's going to have, the first half is going to be sort of work from 2011. The second half is going to be work from 2015. And the last half is going to be work for the future, which is somewhat shorter than the first two halves. So this is, in some way, the original streaming problem. I don't know how many people recognize the characters. This is Christopher Robin here. This is Winnie the Pooh. This is Piglet. And they're playing the famous game of Pooh Sticks, which I think was invented somewhere near where I'm from. And in this game, you stand on a bridge over a stream, and you drop a stick. Or each person drops a stick on one side of the bridge, and you run to the other side of the bridge. And the first person to shout out that they see their stick come under the bridge is the winner. It's a real-time problem. It's no good saying after the fact, well, I'm sure my stick came first. You have to shout it first. So basically, it's a real-time streaming pattern matching problem. And that's the kind of thing which we can try and prove low bounds for. And it's sort of under a general interpretation of the word pattern matching. Because this is going to be an unconditional lower bound talk, we have to define a computational model. And for those who don't work in the area, I'll try and define what the CellPro model is. That's the standard model now for proving unconditional lower bounds. So the CellPro model is really rather simple. The idea is that you have some memory, and each cell or word of memory takes W bits, and you can read and write stuff to memory. But the trick is that all computation is free. The only thing we're going to count are the number of reads and writes to memory. So we imagine that the running time of an algorithm is the amount of time it takes to do computation plus the amount of time it takes to read and write stuff to memory. So if you prove a lower bound for one half of that sum, you've proved a lower bound for the whole sum. So in other words, the CPU, as it were, the abstract CPU has infinite computational power. This is infinite, which requires infinite cooling, but we don't worry about practical aspects here. This is an abstract problem. But the idea is that we're just going to try and prove lower bounds for the number of reads and writes, assuming that all computation is free. That's the general model. And the idea is this gives us a lower bound. The CellPro model will give us a lower bound sort of in any sensible model of computation that we are interested in. So in particular, the RAM model, I suppose. We want to make our lower bounds as general as possible. So that's the model. Now, of course, lower bounds in the CellPro model have existed for a while for data structure problems. So the CellPro model was in some sense introduced by Minsky and Papert, I think, in the 60s, but really by Yao in 78 in the setting that we're interested in. And data structure problem lower bounds, or data structure problems in general, sort of come into two categories. There are static problems, so this is problems that are largely looked at the predecessor queries. So in other words, here you pre-process the data and you have to do some queries. These are query-only problems. And we see papers by Itai, Milton, Paul Beam, and others there in this list. And then in 1989, really lower bounds for dynamic data structure problems really sort of kicked off with this seminal work of Fredman and Sachs, who just introduced a proof technique that people didn't have before. So in a dynamic data structure problem, you have queries and you have updates. So the first thing, you have queries only, then you have queries and updates. And here we see a list of papers. The idea of listing these papers is not so much that you will look at each one individually, is that between 89 and the early 2000s, this is a reasonably large proportion of all the papers that were published in this area. Even though they all, in some sense, use the chronogram technique, just having the technique doesn't make it very simple for a particular problem to actually be able to prove a lower bound. There's a significant amount of work to be done. So then you will see, and then in 2000, the key point about this is that the chronogram technique, the best possible lower bound you can prove using this technique is log over log log. I should have said that. The technique simply doesn't allow you to prove anything higher than that. Generally speaking, you look at log over log log, different epochs of time going at the past, and you argue you need at least one bit from each one of these epochs. There's nothing you can do to get anything higher than that using this technique. And in 2004, the great late genius Mihai Pușescu, I'm delighted to see his name being mentioned in sort of every other talk in this workshop, as so he should be, along with his supervisor, Eric Domain, invented a new technique, which he called the information transfer technique. And this had two great advantages. First of all, the log over log was turned to log, which meant that some data structure problems now had tight bounds, because that was the same as the upper bound. But secondly, it's just a different way of looking at the problem, the proof technique. It's beautiful, in my view. In some contexts, it's a lot simpler, and it's the technique which we're going to use in this talk. And then between 2004 and 2015, really the next, and I think the last, so far, great advance was done by Casper Larsen, who showed that in some cases, in fact, you could revisit the chronogram technique and soup it up in all kinds of clever ways in order to improve this log n to log squared. In our case, our upper bounds, at least within the model, will be log, so we unfortunately can't use Casper's techniques for these particular problems. But they are rather wonderful. So let's try and define a problem, which I haven't told you a problem yet, other than playing acoustics, and then we can see what we can do. So remember, this first half is talking about work from 2011, and then we'll move on. So we're going to look at it as a streaming convolution problem. Mathematically, more properly, it's called cross-correlation, but I gave up with arguing with the community, so I'm going to call it convolution. And in this problem, we're going to have a fixed vector here of some length. It happens to have 8 elements in it. Each element of this, both the vector and the stream, comes from some range, 0 to q minus 1. And we have a stream that comes in one symbol at a time. And each time a symbol comes in, we have to output the inner product between the fixed vector and the last n-length suffix of the stream. And we have to do this before the next symbol comes in. So, for example, this symbol comes in, we have to output the inner product between v and x3 to x10. Next symbol comes in, we have to output the inner product between v and x4 to x11, and so on and so forth. So the question is basically, how long does that take? Obviously, naively, you could just compute the inner product, right? That would be, if n is length of v, then it will take you n time. So we showed, this is me and Marcos Jalsenis now, a lower bound for this problem of delta over w times log n. In fact, I can give you the complete proof for this lower bound in the next 10 to 15 minutes. And here, just remind yourself what these things are. N is the length of the vector. W is the number of bits in a word, and this delta here is the number of bits needed to represent a symbol. This is kind of crucially important. And the interesting case is when W is like log n, because we like these words to be big enough to be able to address memory. Right? And when delta is roughly the same size as W, then we have a lower bound of log. Then we're happy. In fact, the technique which we used 2011 requires W to be as big as log n. The proof simply doesn't hold otherwise, but then later on we managed to relax that slightly to allow us to reduce W if we really wanted to. But the case we really care about is when W is like log n. Right, so I've already suggested, of course, there's a simple linear time per new symbol algorithm, just to compute the inner product. But actually, you can do better than that. In 2011, together with Efremenko, Part, and Porat, we showed a general method for reducing a whole range of these online problems to offline problems. And the formula you get is take the complexity of the offline problem. So in this case, this is cross-correlation or convolution. So you do it by fast Fourier transforms and n log n time offline. Divide it by n and multiply it by log. There's your formula. So in this case, we take the n log n, divide it by n, multiply it by log, and we get an algorithm which takes log squared time per new symbol. Every time a new symbol comes in, it takes log squared time to output the new inner product. In fact, if you look back in the literature of the 1970s, and you can read papers using analyzed the context of Turing machines, you'll see that some of the ideas in here, in fact, are also in this paper of Fisher and Stockmeyer from 73. So now we have this lower bound, which I'm going to prove to you completely, of like log, and upper bound of log squared. So there's a gap. Right? So can we seal the gap? Well, this is tricky. Because, first of all, in the CellPro model, remember where computation is free, offline, the algorithm is linear time. Just read the data in. It's a very odd thing to do. The CellPro model is not designed for offline things, but nonetheless, just read the data and you get the answer. And using the same reduction here that we just talked about, to make it online, we divide by n and multiply by log, and we get a log time algorithm in the cell probe model for the online version. So in fact, our lower bound, when w equals delta, is tight in the cell probe model. So then you might say to me, yes, but this cell probe model, Raphaël, you've come along with, it's clearly no good. Get me a better model, and I'll be able to prove you a higher lower bound, maybe include computation somehow. But this turns out to be tricky too, because by the same reduction, any better online lower bound than log would imply an offline lower bound above linear for multiplication or convolution. And that's already a very significant thing to have done. So it seems tricky to improve this lower bound. The only route that we seem to have available to us is to try and improve this upper bound, but don't know how to do it. So that's the status there. Right, so how are we going to do it? Well, we do it, of course, the way people always do things. We're going to apply Yau's minimax principle. We're going to, in fact, find some random input distribution for which there's a lower bound for any deterministic algorithm, which would imply that there exists some worst-case input distribution, or deterministic input distribution, for which there's a lower bound for any randomized algorithm, which, of course, implies a lower bound for any deterministic algorithm. So we're going to focus. What we actually do is this thing up here. What we get is the thing down there. So let me try and describe the information transfer technique. But first, before I do that, now I'll describe the problem. If you remember, we talked about data structure problems which were query only. Those were static ones. Data structure problems which were query and update. But our streaming convolution problem is neither of those. There are no queries. There are only updates. So this is really a third type of problem. And it's kind of important to understand that it's not the same as a standard dynamic data structure problem. This is an update-only problem. In fact, it has another feature which will be relevant later on. It's an update-only problem where there aren't any indices either when you update. You don't say to update position 23 or something. You just give it a new symbol. So it's a restricted form of update-only problem. Type of problem that hadn't been considered before, but nonetheless it turns out that Mihai's information transfer technique, the beautiful thing it is, applies pretty much directly to this model. So
again, after an update, the system is supposed to answer the most recent input.
Exactly.
Immediately.
Exactly right. Yeah. No, that's right. No options, no queries. No, nothing. Just gets a symbol in, gives an output. That's it. But Mihai's lovely method turns out applies beautifully to this problem. So let me describe it to you in the way we think about it. In this update-only setting, which is just marginally different from the way it's written up, but it's the same idea, just got it written with different colors. Right, so here you have the memory here, and we're going to have here, this is the stream. For the moment, we're going to set everything in the stream to be fixed and known, and everything in our fixed vector to be fixed and known. I always forget to ask, I'm assuming this is green, this is blue, I'm colorblind. Good. So symbols come in, and we give outputs. Because everything's fixed and known, nothing's very interesting happening. Eventually, we're going to talk about a region of things which we're going to say are unknown, or they're going to be chosen uniformly at random. So some unknown symbol comes in. Remember, every time a symbol comes in, we give an output. Every single one, right? When this symbol comes in, we give an output, an end product. And we have to do something to do that. So our algorithm, whatever it is, writes somewhere. In this case, for example, it writes to that cell of memory. Another symbol in, it has to do some computation, whatever it is, which is free in our case, but it has to write somewhere in memory to give an output, and it writes to 2 more cells of memory. Another symbol comes in, it writes to 1 more cell of memory, and then another couple, I think. Right. So over that period there of length L of time, the symbols that came in order to give those 4 outputs it had to give, it wrote some stuff to memory. So we read some more symbols in. Now these are going to be fixed and known ones. All our unknown things are just these question marks. And here it reads some cells of memory. It happens to read these 2. That's fine. Another symbol comes in, reads another cell of memory. This time it happens to read one that was written in the previous period of time. Does it again, reads a couple, another one that was written beforehand, and does it again. And what we're going to be interested in is this set of cells here. It's a set of cells that were written in the previous period of time, corresponds to L inputs, and read in the successive period of time, corresponds to L outputs, and not overwritten in between. And this is what's called the information transfer. It's information that's going to be transferred from this period of time to that period of time. And that's going to be the key tool that's going to be used to prove the lower bound. So first of all, we need to persuade ourselves that everything that we need to know about this period, about these 4 symbols, is encoded in information transfer. We only need to know about these cells here. We don't need to know anything else about these symbols whatsoever. And we're going to persuade ourselves of this. Then what we're going to do is we're going to argue that, well, we all know, of course, that the entropy of any random source is, an upper bound on the entropy of any random source is the size of an encoding of that random source, or the expected size of the encoding, right? So we're going to argue that the conditional entropy of the outputs given this period is going to be something in terms of the expected information transfer. It's going to be written by 2 times the word size plus the word size over there. So this is going to give us an upper bound for the entropy, and then we're going to get a lower bound for the entropy later on, which is going to give us a lower bound for this information transfer. That's the technique that's going to happen there. So how can we establish this inequality here? Well, we just give an explicit encoding for it. And the explicit encoding is the most obvious one you can think of. For the information transfer, what we do for every cell, we store its address and its contents. So W bits for each one of those. That's where the 2W comes from. And we also have to store the length of the information transfer so we can actually decode the thing. So that's an encoding. Now, of course, is it good enough? Well, can you actually use it? Can you decode? It's all very well saying on encoding, but can you actually decode using it? So, and to persuade you can decode, let's do it. So imagine we have our algorithm, we simulate our algorithm running along here with the symbols coming in, and it gets to this point here, and it's going to jump over and carry on from there. Right, so it doesn't read any of those things in, it just has this encoding of the information transfer. So it gets to this point here. Every time our algorithm does a read, it's going to look at information transfer and see if that address it wants to read is in the information transfer. If it is, it just reads the contents. Every time it does a write, over here, it's going to look at the information transfer and see if that address is there. If it is, it wipes it out, and then it writes to the correct place in memory. So from that argument, hopefully we believe that this encoding is sufficient to be able to give us all the information that we need from this unknown region in order to answer questions correctly afterwards. Now, of course, this was an upper bound of the entropy. We want a lower bound of the entropy as well. Now, this, of course, depends on how much information we actually need to know about this. That was sort of sufficient. We have to worry about necessary now. Depends on what this fixed vector is. There exist fixed vectors for which we don't really need to know anything about that at all. Now, I notice there hasn't been a lot of call and response going on. I'm not sure if I'm brave enough to do it, but if someone wants to answer, what would be an example of a fixed vector here for which we don't need to know a single thing?
0.
Zeros, thank you very much. I'm very grateful. Great. So if it was all zeros, you wouldn't need to know anything about it at all, right? So you wouldn't get a low bound at all for the entropy. That would be a disaster. So there are other fixed vectors for which you need to know something, but not too much. Imagine the fixed vector was all ones. Well, then we certainly get something like delta. Remember, delta is the number of bits needed to represent a symbol. Bits of information for the first output here, right, we need. But it's the same delta bits of information for every output afterwards. So for all 4 outputs, all outputs, we only need delta bits of information from this to be able to answer things correctly.
Anything with a small period.
Yes.
Be compressible.
Yes. So we can construct, though, without too much difficulty, a fixed vector that's going to do much better. So here we have a fixed vector with 1s at power of 2 positions, starting from the right going left. And I'll just demonstrate to you, and I'll double the length of the unknown interval to make it easy to see what's going on, that this will require us to know a lot about unknown interval. So let's just look at it. Right. So here we give some output, whatever it happens to be. Another symbol comes in, gives some output, whatever it happens to be. We're going to ignore these for the moment. Right, let's get to here. At some point, we get to a situation where there's exactly 1, 1 from the pattern aligned in the unknown interval. At which point, remember, we know all this dark green stuff. We know everything in the fixed vector. So given the output, we can infer exactly what that is, just by subtraction. Right. So the output tells us precisely what that is. And the next shift along, we get to find the next symbol, and the next symbol, and the next symbol. So we get to learn half of the information from this interval, at least. Maybe the other outputs told us some more stuff, but don't worry, half at least. So the conditional entropy of our output is going to be at least half of the entropy of that interval. Entropy of the interval, of course, is L delta, because each symbol's got delta bits, and they're uniform at random. So it's at least L over 2 times delta. So now we have our lower bound for our conditional entropy. And so what we have to do is just plug in the upper bound and lower bound and solve. And we see that the expected conditional entropy of the information transfer is going to be at least delta L over 4W minus a half. So this is great. We made a lot of progress. Of course, we don't really want conditional entropy, right? This is a bit funny. Things are being fixed. But we can fix that too, very simply, just by no longer fixing all this dark green stuff, but just making it also uniform random, everything uniform random in the stream. And then by the miracle of linearity of expectation, we get the information transfer, as opposed to the conditional information transfer. We get the same low bound for it. So now we know that the information transfer is at least delta L over 4W minus a half for every interval of length L. Of course, we have more than one interval of length L, right? So we're going to do about it. And what you do now, we want to sum over lots of intervals length L to get the lower bound of the information transfer for the whole thing, right? And we do this using what's called the information transfer tree. We just consider consecutive intervals of time, consecutive intervals of power of 2 length, and look at the information that's transferred from each interval to the consecutive one. So that's some of length 1 to the next one. Then we can see we also have something of length 2 to the next one. So I'll just go through this quickly. So this tree shows every one of these nodes you can think of having information transferred from its left tree to its right tree. And so what we need to do is just sum the information transfer for every one of these nodes, and that will tell us the total information transfer. And you might worry for a second that if we just literally summed over the nodes somehow we're double counting. There's no double counting. Kind of the easiest non-mathematical way I think of thinking about that is just imagine dropping a vertical line from each one of these nodes and looking how many times we count information transferred from the left to the right, and it's exactly once for each one. We just sum over the nodes. So the expected number of cell reads is at least the expectation of the sum of the information transfer, which is at least the sum of the expectation of the information transfer, for which we already have this lower bound. We plug it in, and we get delta over W times n log n for n inputs, which gives us the promised delta over W times log n amortized lower bound. So that's a complete proof for unconditional lower bound for online convolution. So after this work, 2013, now with Benjamin Sachs, we went on to look at the same problem, same model, with Hamming distance. So now the symbols are still non-binary. They won't be binary either in the fixed now string. And we get the same lower bound, but it's much more difficult. And why is it much more difficult? It's much more difficult because you have to construct, again, some some hard fixed string and some input distribution, which is going to give us high entropy for these outputs, which turned out to be relatively simple in the case of convolution, but Hamming distance is much more difficult. Intuitively, why is it much more difficult? Because if you take two symbols of the log n bits and you ask, do they match each other, that tells you one bit of information. If I multiply them, it gives you much more information, right? It's just much more technically difficult to find the hard distribution, but nonetheless, we achieved it, which is good. And then, as I say, we also did some work to show that actually you could reduce W from log n, which this particular proof technique doesn't allow you to do. So that was nice, and we're pleased about that. And that's the state until about 2015, let's say. But what happens if the input-output is binary? Bit streams, right? They're not such odd things. Stream comes in one bit at a time. Let's say our vector is binary as well. Every time a new symbol comes in, we want to give an output, right? Well, the lower bounds of delta over W times log n are not so good anymore. Because remember, we really want W to be log n. So we set delta to 1, we get log n over W. If W is log n, we get nothing. And there's nothing you can do about it. Because you can't get more than n bit or L bits of information out of L bits, right? there's nothing you can do about it. That's just what the technique gives you. So you might think at that point, well, that's bad. Maybe I just won't mention it to anyone. Then you might have a look at it and think, well, you know, we were doing these outputs sort of mod q, which q was the range. I guess it's n in this case. What happens if we don't sort of take mod anything? Let's look at convolution for the moment. We'll stick with convolution just for a second in the products. The values we output are, if we don't take mod anything, are between 0 and n. So potentially they have something like log n bits of information each output. Potentially, might do. So potentially, if I just look at n over log n outputs, as opposed to n outputs, or L over log L if you're looking at the interval length, then potentially the entropy of L over log or n over log n outputs could be linear in n. In other words, maybe we don't actually have to look at the same length of outputs as we do inputs. We can look at some shorter length and still learn some constant proportion of the n bits. But then if you do that, of course, the proof technique doesn't work anymore because there's no information transfer tree anymore because these things are not symmetric anymore, and you've got problems with double counting, potentially, all the rest of it. But then you have to try and find a problem for which you could possibly apply these ideas. So that's what we did. So then we're going to move away from convolution for a minute. We found a problem, and the problem is called pattern matching with address errors. It's introduced by Amir and others in 2009, I think. And it goes as follows. In a classic pattern matching problem, you have two strings, and you imagine some error has been applied to these strings, and you want to know, basically, are they within some distance of each other? So the error has been applied normally to the elements of the strings. In the pattern matching address errors idea, then you imagine yourself a telephone operator, maybe some way, maybe it's a stretch, and it's not the errors are in the symbols in the strings, the errors are in the indices in the strings. The thing's just jumbled up somehow. So let's imagine the message that's sent is 11 plus 2, and what you receive instead is 12 plus 1. A happy coincidence, nothing too bad happened as a consequence of it, but you will notice that 11 plus 2 is an anagram of 12 plus 1. Right? This T has been moved over there, that W has been moved over there, this E has been moved over here. And you might want to measure the distance in these two things, and that's what they do. They talk about a distance between two anagrams, essentially. Now, the name which they chose was L2 rearrangement distance. I think I might have called it anagram distance, because it's too long, but there you go. And broadly speaking, I mean, mathematically, one of these things is a permutation. The other thing, if it isn't, the distance is infinite, I think. And you just minimize over all the possible permutations the sum of the squares, the distances the symbols had to move. That's the LT rearrangement distance. And to give a concrete example, this is a bit simpler to look at, maybe imagine that the two strings are 11100 and 10110. Then it turns out you just have to move each bit to its nearest bit in the other string that hasn't already been used. So this 1 doesn't go anywhere. So you get 0 squared for the distance of that one. That 1 goes 1 place. You get 1 squared. That 1 goes 1, because you can't go to that one, it's already been used. It's 1 squared. I think this 0 has to go back 2 to get to there, and the last 0 stays still. So the L2, that's just L2 rearrangement distances. Together with Benjamin Sachs, we showed this can be solved in log squared time online. Our general reduction, which I talked black box reduction, doesn't work for this problem, but we found another way of making this thing online. So this was in SODA 2009. So for this problem, we can solve the steps set up before and show a lower bound. So for binary inputs, our new lower bound is now going to be log squared over w log n, which is interesting when w is log. So that's basically log over log log. To do this, we have to find some input distribution so the conditional entropy of the outputs is high. And we also have to find some way of summing these information transfer. Now we don't have information transfer tree anymore without double counting, so we can actually get the full information transfer. Right. So I'm going to give you just a general idea of how to do this, because it's quite technical, but I'll just give you a general idea how we do this. So the first thing is how do you do the information transfer argument now? Just imagine the entropy part was solved. Right. So imagine that we've solved this part. We want to do this part. And the trick is to introduce gaps. So previously, we talked about a transfer information from one interval of length L to another interval of length L. In this case, we're going to talk about transferring information from one interval of length L log L to another interval of length L, but there's a gap between the two things. So there's a risk that the information, as it flies from here to here, might fall down the gap. And these L's are going to be taken, unfortunately we can't take all power of 2 length L's anymore. What they're going to be, they're going to start around n to the quarter, and then go to about, I think, n to the half, and go up in factors of log squared. And we're going to have log over log log of them. This is why you get log over log log rather than log in the end. But that's the general idea. We're going to try and argue about the amount of information that's transferred from this interval to that interval. Remember, this is shorter than that, but there's a gap in here, and we want to argue that it's going to be some constant proportion of L log L information has to be transferred to this shorter region of time. And if we do that, then we get something very similar to what we had before. So now this is the conditional entropy of the output, so I've called A for some reason. Given this is the dark green fixed stuff, is fixed. We're going to have an upper bound of roughly, of 2W plus 2W times the expectation of this thing, which is the information transfer from the first interval to the second interval, plus the information transfer to the gap, given the fixed stuff is fixed. And then the lower bound, we're going to have exactly what we want, which is we're going to have that the conditional entropy of the outputs, given the fixed stuff is fixed, is going to be at least L log n times some constant. So this is the object here. This is to get this, you need to find the hard distribution, and to get this, you need the new technique. So what can we say about that? Well, then we're going to do the same thing by doing the expectation, and we're going to end up with conditioning over by taking expectation, to get rid of the conditional expectation. And then we have the information transfer, so the expectation of the information transfer is going to be bounded below by L log n over 2W minus this transfer into the gap. Right. So, unfortunately, I won't have time to describe it to you, but you have to argue somehow that you don't lose too much stuff down the back of the sofa, which you can do, it turns out. It's relatively simple if you're interested in only worst-case lower bounds. It's slightly more involved. You want amortized lower bounds. This is what we do want, unless you can do that. But then it's still a bit awkward, because we've got to worry about this sort of how we're going to do these sums so we don't double count stuff. So you have to choose. So we're going to sum over all these intervals that I've told you log over log log with them. But we can't just start anywhere we want to start. So we have to very carefully start some subset of the starting times. We're going to sum over. So that in particular, it was quite fun. So what you have basically is that one interval ends up in the gap of the previous interval in this hierarchy. And so you end up with this bound here. So let me try and give you a clue. Right, so that's the technique, which I've kind of hand-waved my way through. Oh, and that's a chap dropping some information through the gap. I think he just about makes it to the other side, so it's all going to be OK. But let me try and give you some clue in a slightly scary slide about what the hard distribution is. And this hard distribution is really the trick. I'd just like to give some idea of what the trick is, because the trick is kind of important. And the question is going to be, can we use it to prove low bounds for any other problem? Some idea. So not scary yet. It'll be scary in a second. So the stream is not too bad. The stream is just going to be a succession of 4 bits blocks, and each 4-bit block is either 0101 or 1010. Right? That's uniformly at random, nice and simple. Independently. The fixed text, this fixed string, is turned into F because it's a string. This is the stream. Is much more complicated, but let me give you some ideas about it. So it's going to be sort of sub-partitioned into different parts. We have various bits of padding, but let's try and just focus on these different parts of this fixed string, which I've called F1, F0L, F2, F1L, F2L, so on and so forth. It's going to be designed in such a way that when we're given an output, remember, every time a bit comes in, we give an output. The output is going to be some number between 0 and n. Well, actually, not between 0 and n. It's going to be some number log n bits. So here's, for example, an output. Let's say the output was 9. And what we want to do somehow is we want to argue that every output tells us about log n bits of the stream. So we're going to look at the separate bits of the output. The bits, number 9 is 1001, hopefully, assuming my math is correct. And what we've done is we construct this fixed string in such a way, because these are all going to have sort of exponentially different scales in some sense, which I won't have time to explain, that the contribution to this output is going to be at exponentially different scales. So this thing here, depending on what this bit of this stream is, whether it's 1010 or 010001, will contribute to the first bit. And this thing here will contribute to the second bit of the output, and this will contribute to the next bit of the output, and this will contribute to the next bit of the output. I think I was counting right to left there. So by designing this thing very carefully, we can ensure that the individual bits in the output are going to tell us 4-bit blocks in the stream. Each 4-bit block only has entropy 1, because it's only got the option of being one of 2 possibilities. So we were able to argue that you could recover some constant fraction of log n bits of the stream from each one of these outputs. So that's the basic idea of how it works for L2 rearrangement. I'm happy to discuss more details anytime anyone wants to know. So that's the end of the L2 rearrangement part. We were able to design this new technique involving the gap, this lopsided disjointness, this sort of rather tricky hard distribution, which enables us to use the individual bits of the output to tell us separate bits of the stream. So to finish, let's go back to what's the first question. What happened to convolution, right? I all of a sudden stopped talking about convolution. So now we've moved from 2011 to 2015, now moving to the future. This turns out to be rather difficult, and perhaps surprisingly so. Let's imagine that the input is binary uniform at random. Right? Fundamentally, it turns out to be this simple mathematical question, which I'll make slightly more exact in a second, turns out to be very difficult to solve. What is the entropy of n over log n consecutive inner products, where consecutive means you slide your fixed vector along by 1? Now, I believe it's linear, but it doesn't seem at all obvious how to prove it, and anybody has any ideas how to do that, I'd love to hear it. So let's put it slightly more mathematically. Let's imagine that our stream is just 1, 1, 1, 0, 1, 1, 1, 1, and n is 4. So the consecutive windows we're going to do inner products with are going to be 1, 1, 1, 0. The next one here is 1, 1, 0, 1, then 1, 0, 1, 1. Right? So we can write those as rows of a matrix from bottom up. And if this thing, we have some random variable here, which is just binary vector length L, chosen uniformly at random, do there exist L over log L by L, by which I mean for a kind of all L, let's say, or an infinite number of L's, terplets matrices? So this thing is terplets because the falling diagonals are constant. So whenever you do this thing with these sliding windows, like these rows, you're going to end up with a terplets matrix, such that the entropy of mx is linear. So there's the open problem. Straight math question, which doesn't seem at all obvious, at least to me. And thank you very much.
Any questions?
So this is a good question. What's H?
Entropy.
Oh.
Entropy. I did want to look up why it was H. I can't remember anymore. Any answers?
Have you investigated conjecture just experimentally?
Yeah, a lot.
And I mean, it seems true for.
I can't find any evidence that suggests it's not true. That's as far as you could do, right?